Hello, this is TCG and welcome to the 7th lecture for the CompTIA Security Plus 601 exam. Let's get started. Cryptography. Here are some basic terms. Plain text. Plain text is the original and readable data that needs to be protected from outsiders. Ciphertext. Ciphertext is the encrypted plain text, unreadable to anyone without the proper decryption key. Cipher. Cipher refers to the algorithm used to perform encryption and decryption. Cryptanalysis. It is the study of analyzing and breaking cryptographic systems. It involves finding weaknesses in the encryption methods and recovering plain text from ciphertext without knowing the key. Keys. Keys are secret values used in the encryption and decryption process. The security of encrypted data relies heavily on the strength and secrecy of the keys. Longer keys tend to provide stronger security, and smaller and weaker keys are made stronger using key derivation functions or KDFs. For key derivation, we use libraries such as bcrypt or libsodium. Homomorphic encryption. Homomorphic encryption refers to being able to perform calculations on the ciphertext instead of having to decrypt and re-encrypt the ciphertext. The result of the calculation on the ciphertext is stored as another ciphertext. Since we don't have to decrypt and re-encrypt the ciphertext, it saves us some computation time and makes sure that the ciphertext is secure. Symmetric and asymmetric encryptions. In a symmetric encryption, we use the same key for both encryption and decryption. Although it is faster than asymmetric encryption, distribution of keys may be risky at a higher scale. Asymmetric encryption. In asymmetric encryption, we use a pair of keys, a public key for encryption and a private key for decryption. A public key is used for encrypting data or verifying a digital signature. It can be distributed openly. A private key is used for decrypting data or creating the digital signature. It must be kept secure and within the system. ECC or elliptical curve cryptography. In this kind of cryptography, we use the mathematical equation of an ellipse to encrypt and decrypt a plain text. ECC is very popular because it offers faster computations and low power consumption, which is why it is used in mobile and IoT devices quite often. Hashes and digital signatures. Hashes are fixed length strings of characters generated from input data of any size. It is difficult or nearly impossible to reverse engineer or to get the original input from the hash. Hashes have something called an avalanche effect, which means that a small change in the input text or the input data can lead to a huge effect in the hash. Collisions. A collision occurs when two different inputs produce the same hash output. This can be exploited to subvert data integrity checks. Digital signatures. A digital signature allows us to verify the authenticity and integrity of any file. It is always attached at the end of the file. It is created by hashing the file and encrypting it with a private key. On the receiver's end, the signature is decrypted by the public key. The hash value of the file is calculated and compared with the decrypted hash value. We will see more about digital signatures in the upcoming lectures. Cryptographic keys. When we talk about the strength of the keys, longer keys are generally more secure. Most algorithms nowadays use 128 or 256-bit long keys. Key exchange. Since keys can be used to decrypt any data that we have encrypted in our system, we need to make sure that it is distributed without any leaks or mishaps. Keys can be distributed out of band and in band. In out of band, a key is sent over to the telephone or in person or in some other ways, but not over the network. It is the opposite in band, in which the key is sent or saved on the network and is generally encrypted to protect it from any outsiders. Real-time encryption and decryption. It refers to the encrypting and decrypting data without any delays. In this case, a symmetric key is made by the client, encrypted with the server's shared key, and the session key is used to encrypt the data. The session key should be changed often in order to prevent session hijacking and man-in-the-middle attacks. In traditional web servers, we use only one key that encrypts all the symmetric keys. This one key can be a big point of vulnerability, which is why nowadays we use perfect forward secrecy or PFS. PFS ensures that even if a key is compromised, past communications remain secure. PFS uses elliptic curve or Diffie-Hellman ephemeral to decrypt and encrypt all the data. Each session has a unique key and is difficult to crack because it requires more computing. Steganography. Steganography refers to the practice of hiding data within other non-secret text or data. It can be hidden in text, videos, images, or even audio files. Unlike traditional cryptography, steganography obscures or hides the existence of the message itself. Various techniques can be used to conceal information in digital media, such as a network based steganography. It involves hiding information within network traffic. This can be achieved in a few ways. Protocol manipulation, which is embedding data within headers or payloads of network packets, modifying the timing of packet transmission to encode information, and utilizing unused fields in network protocols to hide data. Image steganography. It hides data within digital images. In most cases, in image chromatography, we alter the LSB or the least significant bit of each pixel to encode the hidden message. This change is imperceivable to the human eye. Invisible watermarks. Invisible watermarks includes modifying the pixel values or audio samples directly, and is generally used for copyright protection and authentication. Audio steganography hides data within audio files by exploiting the limitations of human hearing. It may include adding subtle echo to the audio or directly modifying the least significant bits of the file. Video steganography hides data within video files, offering large capacities for hidden information due to the combination of audio and visual data. In most cases, we modify the least significant bit of video frames, or we alter the motion vectors in video compression algorithms to encode the data. Quantum computing. Quantum computing leverages the principle of quantum mechanics to perform computations that are infeasible for classic computers. The fundamental unit of quantum computing is a quantum bit or qubit. Quantum computers offer us a new path when it comes to computing, but that does not mean that it is necessarily better than traditional computers. Qubits can exist in superposition, representing both 0 and 1 simultaneously. Just like we have gates in classic computers, there exist quantum gates that manipulate qubits through quantum operations. Post-quantum cryptography or PQC. Quantum computers can potentially break widely used cryptographic systems like RSA and ECC due to their ability to solve certain mathematical problems much faster than classical computers. Which is why we have designed algorithms to be secured against the potential future threats posed by quantum computers. PQC includes various types of algorithms such as lattice-based, hash-based, code-based, multivariate polynomial, and supersingular elliptical curve isogeny cryptography. Quantum communication and quantum key distribution. Quantum communication leverages the principles of quantum mechanics to securely transmit information. Quantum key distribution, or QKD, is a primary application of quantum communication. It allows two parties to generate a shared secret key which can be used for secure communication. It is impossible to create an exact copy of an arbitrary known quantum state, providing security against eavesdropping. Any attempts to intercept or measure the quantum data alters its state, alerting the communication party to the presence of an eavesdropper. Ciphers. Stream ciphers. Stream ciphers encrypt data one byte or bit at a time, often used for real-time data encryption. They are typically faster than block ciphers and require less computation power. They're ideal for applications where data is transmitted in a continuous stream, such as video and audio transmission. Block ciphers, on the other hand, encrypt data in a fixed size blocks, usually 64 or 128 bits, by applying a symmetric key algorithm. They are generally more complex and secure than stream ciphers, and can be used with various modes of operation to enhance security and functionality. When the data size is not a multiple of the block size, padding is required to fill the bits or bytes of the block. Block cipher modes of operation. ECB or electric cookbook is the simplest mode where each block of plaintext is encrypted independently using the same key. It is easy to implement and parallelize, but identical plaintext blocks produce identical ciphertext blocks, making it vulnerable to pattern analysis. CBC or cipher block chaining, it enhances security by XORing each plaintext block with the previous ciphertext block before encryption. It uses an initialization vector or an IV to ensure that the first block is uniquely encrypted, even if identical messages are encrypted. Errors can propagate, meaning a single bit error in a ciphertext block can affect the decryption of subsequent blocks. CTR or counter. This mode turns a block cipher into a stream cipher by encrypting a counter value and XORing it with the plain text. GCM or Galios counter mode. It combines the counter mode of operation with authentication, providing both confidentiality and integrity. It encrypts data and provides a MAC or a message authentication code to verify data integrity. Just like counter mode, it supports parallel processing for high efficiency and high speed. Blockchain technology. Blockchain is a distributed ledger technology that ensures the integrity and security of data transactions across a decentralized network. It is the backbone technology behind cryptocurrencies like Bitcoin, but its applications extend far beyond digital currencies. How it works? Transaction initiation. A blockchain transaction begins when the user initiates a transaction. This could involve transferring cryptocurrency, recording a contract, or other data transactions. Transaction broadcast. The transaction details are broadcasted to a network of peer to peer or P2P networks known as nodes. Each node has a copy of the entire blockchain and validates the transaction. Transaction validation. Nodes validate the transaction by checking if Alice or the first party has the one Bitcoin to send and that she hasn't already spent it. This involves checking the transaction against a blockchain's transaction history. Block creation. Once validated, the transaction is grouped with other transactions into a block. The values are then checked against the validated data in the block. Cryptography use case. Low power devices. These devices tend to have limited CPU and memory resources, which is why we use algorithms designed for low computation, such as ECC. Low power devices also tend to use shorter key lifetimes and efficient key exchange protocols. Low latency applications. Some applications require the least amount of delays, so the encryption and decryption processes must not introduce significant delays in these applications, which is why we use symmetric encryption and smaller keys in these kind of applications. High resiliency. We use redundancy and protocols that ensure data integrity and authentication, such as TLS, end-to-end encryption, and more, to ensure that the data has not been tampered with. Use cases. Secure communications protect the data transmitted over networks. Data protection ensures that the data at rest on storage devices is secure. For important documents, we verify the identity and authenticate any and all important files. Cryptography is used to secure online payments and digital currencies, and to secure APIs and web applications using tokens. It is also used to ensure data integrity and immutability in blockchain. Limitations of cryptography. Finding balance in cryptographic implementations. Poor implementation. Even the strongest algorithms can be compromised by poor implementation. Ensuring robust coding practices, regular audits, and thorough testing is crucial. Implementation variability. Not all implementations of the same cryptographic algorithms are equal. Variations in efficiency, security, and resilience can occur due to differences in coding practices, hardware support, and compliance with standards. Limitations. Cryptographic operations can be computationally intensive, leading to performance bottlenecks, especially on low power or resource constrained devices. Cryptographic keys and outputs can increase the size of data significantly, impacting storage and transmission efficiency. Using weak or poorly chosen keys can compromise the security of cryptographic systems. The time required to encrypt and decrypt data can be significant, impacting real time applications. Cryptographic algorithms may become obsolete over time due to advances in computing power and cryptanalysis techniques. Poorly designed algorithms or implementations can exhibit predictable patterns, weakening the security. Reusing cryptographic keys across different contexts or for extended periods of time increases the risk of compromise of that key. Finally, balancing the need for strong security with limited resources, such as computing power or memory, can be challenging. Secure protocols. Voice and video. To secure voice and video data, such as VoIP calls or video conferencing, we use the Secure Real-Time Transport Protocol or SRTP. Time synchronization. NTP-SEC or Network Time Protocol Secure is an enhanced version of NTP that includes improved security features to prevent tampering with time synchronization. It also helps prevent against spoofing attacks. Email. SMIME or Secure Multipurpose Internet Mail Extension provides us with end-to-end encryption and digital signatures for email, which can help us verify the sender identity and message integrity. Web. SSL or TLS, which is the Secure Socket Layer or Transport Layer Security. TLS is an enhanced version of SSL, and both of these algorithms provide encrypted communication between web browsers and servers. It protects data from tampering and eavesdropping and verifies the user and server identity. IPsec or Internet Protocol Security. IPsec is a suite of protocols for securing IP communications by authenticating and encrypting each IP packet. IPsec is generally used in VPNs or to secure site-to-site communications or both. File transfer. FTPS or FTP Secure. It is an enhanced version of the FTP protocol and is used to secure file transfers between clients and servers. SFTP or SSH File Transfer Protocol is used to secure files sent over the SSH protocol. It ensures the confidentiality of data in transit. Directory service. LDAP or Lightweight Directory Access Protocol is used for accessing and maintaining distributed directory information services. We use LDAP over SSL or TLS to secure LDAP, and we use SASL or Simple Authentication and Security Layer to add authentication support to LDAP. Remote access. SSH or Secure Shell provides network remote login and other secure services over the network which may be secured or unsecured. We use SSH for remote server administration and secure tunneling. DNS. DNSSEC or DNS Security Extension adds security to DNS through by adding digital signatures. It protects against DNS spoofing and cache poisoning attacks by verifying the files via digital signatures. Routing and switching. SNMP version 3 or Simple Network Management Protocol version 3 adds security features to SNMP, including authentication and encryption, securing monitoring and management of network devices. DCHP or Dynamic Host Configuration Protocol securely integrates with Active Directory to ensure only authorized devices receive network configurations. Subscription software. This software allows us to make sure that the software remains up to date with the latest security patches and features. It regularly updates the software to improve security and functionality. It also helps us verify the updates that are in. It also helps us to verify if the updates are integrated correctly and the software's integrity is maintained. Endpoint protection. Endpoints. Endpoints are any devices that connect to and communicates within a network, such as desktops and laptops, mobile devices, servers, IoT devices, and more. Antivirus and anti-malwares. They are the traditional softwares that helps us protect endpoints from malware originating from outside the endpoint device. They detect and remove viruses using signature-based detection. They constantly monitor files and processes for any suspicious activity and can identify new or unknown threats by analyzing the behavior of those files and programs. Endpoint detection and response, or EDR. EDR solutions provide advanced protection by detecting, investigating, and responding to threats at the endpoint level. It actively searches for potential threats within the network and provides tools for investigating and mitigating these detected threats. After the incident is over, they offer detailed information for future references and defenses. Data loss prevention, or DLP. DLP solutions block or encrypt data transfer based on predefined policies. An endpoint DLP protects data on devices by monitoring and controlling data transfers to external devices or networks. Next Generation Firewall, or NGFW. Unlike traditional firewalls, a next generation firewall can act also in the first layer of the OSI layer. Unlike traditional firewalls, a next generation firewall can act on the application layer to control those applications based on policies. They can detect and block complex threats that traditional firewalls cannot detect. They also provide additional security layers like sandboxing and threat intelligence. Host based firewall. A host based firewall controls inbound and outbound traffic and applies rules to permit or block traffic based on IP addresses, ports, and protocols, and other such data. A host based intrusion detection system, or HIDS, monitors the activities on the host to detect signs of malicious activity. It collects data from logs, changes to critical file system, and detects anomalies in order to detect any intrusions on the system. A host based intrusion prevention system, on the other hand, blocks processes or activities that match known attack patterns. They control system behavior to prevent vulnerabilities from being exploited. For example, they can send TCP reset packets in order to stop a reply from a malicious link. Boot integrity. Boot integrity ensures that the computer's process is secure and uncompromised from the very first instructions executed by the system. This prevents malicious code from being loaded during startup and ensures the system starts in a known and a trusted state. We need boot integrity to prevent attacks from rootkits and bootkits. These kind of malwares are designed to load before the operating system and can be extremely difficult to detect and remove. Ensuring boot integrity helps to prevent such threats. There must be a chain of trust that provide a secure foundation for verifying the integrity of the system during the boot process. Hardware root of trust. Hardware root of trust provides an immutable trust anchor, or a starting point that cannot be modified, ensuring the reliability of the initial verification. Leveraging hardware security features that are inherently more difficult to tamper with compared to software only solutions helps us to secure the boot process even further. Trusted Platform Module, or TPM. A TPM is a specialized hardware chip designed to secure hardware through integrated cryptographic keys. TPM securely stores cryptographic keys, certificates, and passwords. TPM records and stores integrity measurements of the boot process, ensuring that any changes can be detected. A TPM also provides attestation services that verify the integrity of the platform to external parties. Doing so protects the system from brute force attacks, and the TPM also helps in cryptographic calculations as it also has a processor and a memory dedicated for the same. UEFI BIOS Secure Boot. This kind of boot only allows signed and trusted software to be executed. It also implements security checks early in the boot process, leveraging the UEFI firmware. Do note that only the manufacturer can upgrade or change the BIOS. A trusted boot verifies each component of the boot process of the OS. Each component in the boot sequence verifies the integrity of the next component before it is executed. Trusted Boot also launches early launch anti-malware or ELAM before checking the drivers to check if the drivers can be trusted. Measured Boot. Measured Boot involves recording all measurements in hashes of all the boot components into the TPM. Each step of the boot process is measured and stored in the TPM's platform configuration registers or PCRs. It also saves information such as platform configuration information, name of the boot device, and more. Database security. Organizations store a lot of data, and this data can also include some customer details as well, which is why the loss of this data can mean financial and reputational harm for the organization, which is why we need to secure our databases. Tokenization. The process of tokenization involves replacing sensitive data with tokens or the process of tokenization refers to replacing sensitive data elements with tokens. Tokens have no exploitable value and are used in credit cards and patient identifiers instead of their real values. Hashing. As we said about it before, hashing is the process of transforming data into a string of fixed length, which is also known as the digest. We cannot recover the original text from a hash. Secure coding. Secure coding is the practice of writing software that is resilient to attacks and exploit. Key principles in secure coding are ensuring that the code has only the minimal permission necessary to function, ensuring that the software fails in a secure manner, and dealing with buffer overflow, since languages such as C or C++ do not deal with it automatically. Input validation. It is the process of ensuring that all inputs to an application are correct and safe before processing. We do that by setting criteria such as the length of the input and the format of the input, etc. By doing so, we can prevent code injection. Dynamic analysis or fuzzing. Fuzzing means testing an application in real time to find vulnerabilities in that application. It is a technique where data is input into the application to find vulnerabilities. Instead of having to do it one by one, there are fuzzing engines that automate this for you. Secure cookies. Secure cookies. Secure cookies are cookies with attributes that enhance their security. One of the attributes allows or ensures that the cookie is only sent over HTTPS. The only HTTP attribute prevents the cookies from being accessed by JavaScript, preventing XSS attacks. The same site attribute mitigates CSRF attacks by controlling where the cookies are sent. HTTP secure header. This header prevents web applications from common attacks. It includes CSP or Content Security Policy and Strict Transport Security or HSTS, which prevents XSS attacks and enforces HTTP connection respectively. It also prevents clickjacking to other websites. Code signing. Code signing is the process of digitally signing software to verify its integrity and authenticity. It uses cryptographic techniques to sign code, ensuring it has not been altered since signing. It also verifies the identity of the code publisher and assures users that the code has not been tampered with. Blacklisting and whitelisting. Whitelisting is the process of only permitting predefined and trusted entities, while blacklisting is the process of blocking specific known malicious entities. Out of the two, whitelisting is generally more secure but more limited than blacklisting. Statistic code analysis is the process of finding vulnerabilities in the source code without having to execute it. Instead of having to do this manually, we use tools such as SAST or static application and security testing